You will not believe the simple steps we can take to create this figure. Draw a triangle and randomly select a point on the interior of that triangle. Then pick any random corner of the triangle. We're going to draw in another point halfway between the corner of the triangle and the random point we started with. Now repeat the process. From that midpoint we generated, pick another random corner of the triangle, imagine the line between them, and draw in the point halfway across. You can do this dozens or maybe even hundreds of times, and you wouldn't necessarily notice the shape you're creating. But as we iterate many thousands and even tens of thousands of times, the same shape emerges every time. Sierpiński's triangle. Sierpiński's triangle is a fractal. What that means is that at any level of zooming in on the shape, we'll see the same shape we started with. This property is called self-similarity. The steps we use to create Sierpiński's triangle in this case have a special name. It's called the chaos game. You can play the chaos game from any number of starting conditions and with any number of ratios. Start with 6 points arranged to make a hexagon, and instead of drawing in the point halfway across, draw in the point 2/3 across, and you get this fractal. Start with 5 points arranged as the corners of a pentagon, and use the ratio 1/5 to generate this fractal. There are many different starting conditions we can use to generate similar fractals, but my favorite is probably the 3-dimensional Sierpiński's tetrahedron. Start with 4 points arranged as the corners of a tetrahedron, and use the same ratio we did for the triangle. That is, draw in midpoints from any random point on the interior of the tetrahedron. What we get is this magnificent fractal. It is possible to play the game in such a way, however, that we don't generate a fractal at all. If instead of starting with the 3 corners of a triangle, we start with the 4 corners of a square and draw in midpoints just like we did for the triangle, we don't end up with a fractal at all. Instead, we uniformly fill the space with points. But even here, we can adjust our rules slightly and generate a fractal. If, as we're selecting randomly among the corners of the square, we never allow ourselves to select the same corner twice in a row, this is the shape that emerges instead. One of my favorite things about mathematics is how we can start with such simple rules and yet generate such complexity.